just some of the common bending moment and shear force diagrams for this kind of structure as well. So say you have a portal frame, wherein the bases of those columns are actually pinned, and then you apply, say, a lateral load, which could be due to wind or seismic or whatever. So in that case, this is the kind of bending moment diagram that we see. And I mean, one thing which I would like to mention is, like, whenever you have to derive any bending moment diagram, always look at the reflected shape of the beam or the structure, because that gives you the kind of curvature that the member is going to have, and that lets you know, like, okay, where you will be seeing, tension at top and tension at bottom and things like that, and therefore you can come up with the bending moment accordingly. For example, if you apply a point, lateral load here in this portal frame, what you would notice is, like, this column here is kind of, flexes, so that there is tension on the inside face of the column, and then there's compression on the outside face. So that's what this bending moment is showing for this column. And then once you go to the beam over there, so the beam would be such that there is tension at the bottom, and then compression at the top. And then these moments which are developed in the columns and the beams are such that the joint over here is kind of an equilibrium. So by that, what I mean is, the bending moment in the column over here and the bending moment in the beam, they have to be equal in magnitude for moment equilibrium of the joint. So that means, for this example over here, like, the moment induced in the beam at this joint and the moment induced in the column at this joint is actually equal in magnitude but opposite in sign. And then once you move to this joint, so if you see here, like, when you apply this lateral force, so this is the bending moment that's developed in the beam, which is going from a negative value to a positive value with a constant slope over here, because there's a constant shear force that's acting on this beam, which we are seeing on this side over here. And then once you reach the column over here, you again see, this bending moment over here in the column joint, and then as you go down at the pin, it actually reduces to zero, right? So what I'm showing here is basically a single storied portal frame, which is subjected to, a point load in the horizontal direction. And then the one below you see is again the same portal frame, but then you have the column bases fixed. So if you see the bending moment diagram, what has changed is, there's this moment which is also developed at the column bases, which was not there here. And this is kind of, the column bending moment diagram and the shear force diagram that we see, right? And then the shear force that we typically, so from a shear force standpoint, so whenever you apply any point load, obviously you are going to see these horizontal reactions on the support, right? So that horizontal reaction that's developed on the support, that's nothing but that's equal to the shear force, or rather the shear force in the column is actually equal to the horizontal reaction that's developed in the support. So for example, if this was a roller support instead of a pinned support, in that case, the entire horizontal reaction would be taken by this support, and there would be no horizontal force or reaction on the support at all. So that means, like, there will be like zero shear force on this member, and the shear force here will be equal to, the total lateral force that's applied. So just wanted to let you know, like, how we come up with, like, how does the moment or the shear force in the column relates to the corresponding reaction at the column. And then something similar happens here, right? Where if you have a column which is fixed at the base, in that case, you will have a moment reaction here, and then you have a shear as well. So you will see that there is a shear force developed here, which is equal to the horizontal reaction at the support. And then the moment reaction that's developed here, that's actually equal to the bending moment of the column at the base. And then it just keeps changing linearly, and the slope of that linear diagram is nothing but that's equal to the shear force that's developed here. So it's the same principle, which is, slope of bending moment is equal to the shear force. So that's the same principle that's applied here as well. The reason I'm saying all of this is because, like, including the, even the boundary conditions here actually are very critical for a frame. So for the same frame, if you had a pinned support versus a fixed support, you see different behavior of the structure, right? So that's that. Now the thing is, if you, in addition to the lateral load, you also see those gravity loads, right? That we talked about before. So in that case, this is kind of the bending moment diagram that we typically see for a pinned base frame, where what you would see is, like, there's a negative moment that's developed near supports because there's fixity. And then you see like this kind of a diagram, which we also saw in a continuous beam. And then after that, there's this moment over here, which is developed in the column, which is equal to the magnitude of the moment developed in the beam here for equilibrium of the joint. And that reduces linearly to zero moment here because this is a pinned support. And this is kind of the shear force diagram that we see here for the column here. So if you see here, the thing is, like, even though we are applying a vertical load, we're still seeing horizontal force here. And the reason for that being is because when you apply this kind of load here, the columns actually want to, move outwards. But then since this is a pinned support, that's actually restraining that movement, and therefore it develops those reactions in the horizontal direction. And that's the reason we see this shear, developed in the column, which otherwise we would not have expected. And then something similar that we are seeing here for a fixed base moment frame. So all of this was for a single storied structure, and then we have like something similar for multi-storied, multi-bay portal frame as well. Wherein, say, if you consider a real life building, I mean, they're more like something like this, wherein you have multiple bays of portal frames, and then you have multiple stories, and then at every story you apply these lateral loads, be it wind or seismic or whatever. So this kind of moment frame is actually, or rather, this kind of moment diagram is what we typically see in a real life building, wherein whenever you apply this load, like you see this kind of so whatever I've shown in green, that's nothing but the bending moment that's developed in the columns. And then whatever is in blue, that's something that I'm showing as a bending moment diagram of the beam. So that's what we typically see for lateral. And for gravity load, say if we consider all of these floors to be loaded vertically, in that case this is the kind of bending moment diagram we get in the beams, right? But and then in reality what we do when we design these structures is we just have those different load combinations based on the different design codes. So we just combine the left diagram with the right diagram based on different load factors. Say if it's a dead load plus wind load, so in that case say the load combination is 1.5 wind. So in that case what we typically do is we just come overlay, or rather superimpose, this bending moment diagram scaled up to 1.5 factor, and then add that or superimpose that with this bending moment diagram here, and then come up with what's the maximum demand that any beam sees at any section, and then ultimately design the members accordingly. But and then this one here is basically for a fixed base condition of the columns, wherein if you see again for what we saw in the single storied portal frame, that we have a similar observation here as well. I mean, we have these base fixities or base fixed moments that's developed here based on the because of these horizontal forces, and then we have when we apply these vertical loads, we also have these bending moment diagram that's developed in the beams and also in the columns. And then again, similar to what we just said before, like all of these are actually combined together or superimposed to come up with the final design aspects. So these were the few items I just wanted to kind of touch upon in terms of the bending moment and shear force diagrams. I mean, obviously this is not really a all exhaustive type of loading. I mean, for example, I just considered the point loads as of now, but then a structure would also see a bunch of uniform distributed load, and that's what typically dead loads and all would be. So they have a more or less similar type of behavior, but the only difference would be like here we are seeing these discrete lines, but then when you consider a uniform load, in that case this will become more like a nice curved type lines. And the reason for that being if you go back to the differential equation that we were talking about, right? The del 4 y over del x4 is equal to loading intensity over ei. So since here there's no loading intensity as such, we don't see that continuity, but once you come up with those linearly varying load or maybe uniform load, you will see much more kind of curved type of bending moments instead of these bunch of linear lines here. Now we can actually quickly just touch upon what are different roles and responsibilities that one would expect an entry level in this industry